Okay, so we just learned about properties of light, and what I'd like to do is show you how we use those properties of light to learn something about the atom. If you remember, different elements emit different colors of light when the electrons are excited, usually in the form of heat. Heat excites electrons and causes these salts to emit distinct colors. So lithium comes out red, copper comes out green, sodium comes out yellow, and also potassium comes out purple. Now, these particular colors help to identify which elements we may be looking at. And the reason is that the colors that come out have to do with the levels that electrons can be excited to. Lithium kicks up the electron a certain distance, and it absorbs that energy, and then when it comes back down, it emits that energy. Since it wasn't a whole lot of energy, it comes as a low-frequency, low-energy red photon. Copper absorbs a little more energy, excites the electron a little higher, and when it comes back down, it gives up that energy in the form of a green photon. Potassium goes up much higher, and because potassium goes up higher, further from the nucleus, when it comes down, it emits a lot of energy in a purple photon. Sodium emits a yellow photon because it goes up to a level that's somewhere between the lithium and the copper. Now, not only do different elements have different colors they emit, different colors can be emitted from different levels that the electron jumps up to. In hydrogen, there's 4 of them. There's a first level, not quite so big, gives you a red photon. Second level gives you a green photon. If you fall down from the third level, we see a blue photon, and if we come down from the fourth level, we see a violet photon. All these colors together kind of look sort of like yellowish white, and if we look at them with a spectroscope, what separates out the colors, we definitely see these 4 bands corresponding to these 4 levels that the hydrogen electrons fall from. So, how does that relate to the Bohr model? What does that tell us? Well, Niels Bohr won a Nobel Prize for proposing that within the hydrogen atom there are 4 shells that we can bump the electron up to. And so the further shells emit purple, then blue, green, and pink. The key thing here was that no other colors were emitted. It had to be in one shell or the other. There's nothing in between. And so what he said was that these energy levels were quantized, meaning there's nothing in between. It's kind of like walking up a set of stairs. You're either on one stair or you're on the other. You can't hang in between. It's not continuous. So we don't see a whole rainbow of colors working out throughout these levels. We only see these very distinct and discrete bands. The problem is that Bohr's model only worked for hydrogen. It didn't work for any of the other elements. So further on, another model develops, the wave mechanical model, that says the electron is not in an orbit or a level. It's a particle somewhere in an area around the nucleus. So we can figure, because there's an attraction between the positive charge of the nucleus and the negative charge of the electron, that it's going to be somewhere in this area. But the electron is constantly moving. At any one time, it could be anywhere within a defined area. We just know there's a higher probability of finding it in one place than another. So we don't know exactly where it is, but it's someplace in here. Usually it tends to be closer, so there's a higher likelihood of finding it close than there is far away. But what this presents is not an orbital or a racetrack or a circle, but really a fuzzy cloud where we just might find the electron. So, I'll stop it here because we're going to talk more about the structures of these orbitals or these fuzzy clouds that we might find the electron in.